Hello, welcome everyone to NPTEL Semiconductor Device Modeling and Simulation course. This is week 13 live session or the course summary session. We will be discussing and summarizing the entire course today, and we look at which topics are very important and some tips and tricks for the coming exam. So this is the entire course structure. So we will go through it one by one across each week's slides. And I've also included here the link to the playlist for the live recording of all these sessions and the link to the notes that we have used in these sessions. So let's start with week one. Okay, so in the first week, we went to the introduction of silicon-based nanoelectronics and device scaling, nanoscale and heterostructure devices, crystal structure unit cell, and Miller indices. So we started with what are semiconductors, what is they whose conductivity lies between insulators and conductors. Why do we need these semiconductors? What is modeling and simulation? So we basically broke down the entire name of the or the motivation of this course. So we started with a simple diode equation, and as well as we looked at the questions on packing efficiency. So these are very important questions. We discussed all the different unit cells: simple cubic, body centered cubic, base centered cubic, and diamond. Diamond is the one which is used for silicon, and we discussed the packing efficiency, which is the volume occupied by the atoms in the unit cell divided by the volume of the total unit cell. So this was important metric, and it is an important point of question in your exams. We did calculations for simple cubic and other different FCC, diamond, and all different structures. We then went to Miller indices. So we determine how do we calculate the Miller indices of a plane. So this is very important for semiconductor wafers, as with different orientations and directions in the silicon, the properties of electrons and holes traveling through the channel change. So their mobilities are different in different directions and across different planes. And the process is also very sensitive to these changes in directions and planes. So it is important to know and identify the Miller indices. So these are more questions on Miller indices and distance between the planes. We did solve questions on estimating the angle between different planes of the silicon crystal. HCP is a very special kind of lattice, and which has six atoms per unit cell. So we determine how where these six atoms lie. Yeah. So this was all about week one, where we mainly discussed about the very basics of semiconductor, Miller indices, and crystal lattices, and yeah, very basic introduction to the silicon nanoelectronics. So let's now see what we discussed in week two and what is important in it. So week two we had questions on reciprocal space, doping, band structure, and effective mass. So we first talked about what is doping, why it is important for us to dope a semiconductor, and we looked at the different kinds of doping, N type, P type, and what is intrinsic semiconductor, what is extrinsic semiconductor. So this is A very basic concept, but very important. So you can expect some questions from this. Then we solve some questions to determine the doping concentration when of p-type when we know the doping concentration of n-type. So we used the law of mass action for it, that is np equals to ni square. That is a very fundamental law for a semiconductor in equilibrium. We also looked at different kinds of semiconductors, direct band gap and indirect band gap, which are used for which emit which have radiative recombination, which do not have non-radiative recombination. So 3,5 materials have radiative recombination and silicon has non-radiative recombination. So 3,5 materials are direct band gap semiconductors which emit light. Then we determine angles of incidence for second diffraction, X-rays of wavelength. So we use very simple formulas for this. We uh, use this optics formula 2d sin theta equals to n lambda to can determine uh, the required angle of diffraction. We discussed what is effective mass and how do we determine it from the EK diagram and where what is its origin. So we started with the Schrodinger's equation, which is a simple 1D Schrodinger equation in which is independent of time. We discussed what is the origin of effective mass, what is its dependency on the curvature, and we came across this that del 2 E by del K square is the curvature. It is inversely proportional to the effective mass. That means higher curvature has lesser effective mass, and flatter EK diagram has a higher effective mass. So this is a very important concept. We also saw this in some other questions where we determined which among A and B which has a lower effective mass. Definitely A has a higher curvature, it has a lower effective mass. Then we slowly tended to see an introduction of the wave function. So wave function has a few properties. It must be continuous, finite, single valued, and its probability must be 1. So among these, sinus is a wave function. So wave function is nothing but the solution of the Schrodinger equation. We discussed the problem of particle in a 1D infinite potential well, and we determined the normalization factor for it, which is uh, if the wave function is a sine kx, so a would be root 2 by L. Then we saw again what is Fermi level. So Fermi level is a theoretical level that helps us to determine the doping in the semiconductor. So for N types, it would be closer to the EC, and for P type, it will be closer to the valence band. We also discussed the impurity level, that is the acceptor or donor levels. So this is the donor level where it donates electrons to the conduction band. That is how we get the electrons from the pentavalent dopants in N-type semiconductors. We briefly discussed what are degenerate semiconductors, where are the ones in which the it are so highly doped that the Fermi level lies above EC. We did some simple questions on based on the carrier density uh, uh, carrier density or doping density equations. Just simply n equals to nc to the power ef minus ec by kt. So this is an important relation. Now let us move on to the next week. In week 3, we discussed density of states, electron mobility, semiconductor statistics, Fermi-Dirac function, and carrier concentration calculation. We started with drift velocity, its dependence on mobility and electric field, and we determined the drift velocity based on some questions. Then we saw the relation between the drift current and drift velocity. It is nq mu e, where mu e is drift velocity. So if we know Vd and the carrier concentration, we can find out the drift current. Then we saw the relationship between the conductivity and mobility. Conductivity is sigma. Sigma is dependent on the carrier concentration and its mobility, mu. So for a semiconductor with both n-type and p-type carriers, it is nq mu n plus pq mu p. So this is the important, very important relation that we should remember. We also saw the relationship between that is uh, the difference between EF minus EI. That is simply KT by QL and ND by NI is important. We discuss what is the Fermi energy function. Uh, this function gives you the probability of finding an electron at an energy level E. So this is how the Fermi distribution looks like. And at E equals to F, the probability of finding the electron is 1 by 2. Then we saw some more questions based on density of states and effective mass. So here we determine the density carrier ratio of density carrier concentration of two materials. Uh, when we knew the band gap of them, so we determined the relationship between band gap and intrinsic carrier concentrations. This is the formula for effective density of states, this NC. And this is the relationship to determine the variation of EI with temperature and effective mass of electrons and holes. So generally we just consider EI to be the middle of the band gap. This may not be always true, so this needs to be taken into consideration, the second part. So it is dependent on mass of electron and holes as well as the temperature that we are working on. Then we saw a negative differential resistance in gallium arsenide, which is due to the satellite values. So here again we have a simple question between for conductivity. We saw some relationship between 1D of 1D, 2D, and 3D DOS, which one, how, and their dependence on the energy. So 1D has 1 by root E dependence, 2D DOS is independent of energy, and 3D DOS has root E dependence. So these are very important relations. Again, some questions on current density and drift velocity. Some questions about the probability of finding electrons. That's due to Fermi. energy. Okay, so let's now go to the fourth week. In week 4, we have more questions on PN junction, IV relations, minority carrier diffusion equation, non-idealities, generation recombination. So we saw what is peak depletion in PN junction and the equation NAXP to NDXN, which is always true. Then some question based on simple diode equation and the reverse saturation current. We saw how do we draw the band diagram. So N plus type has lower energy than P type. So if we are given these kind of configuration, we can draw some rough sketches of the band diagram. So this is extremely important. We then calculated built-in potential from the electric charge profile. So these derivations that come from the Poisson's equations are important. We saw uh, how BJTs are biased, what are different regions of operation, saturation and active regions, and what is the relationship between uh, the current gain of a BJT with IC and IB, and how the different regions of operation affect the BJT operation and the uh, beta. Then we saw some question based on the correct relationship between the built-in potential in the two junctions in the BJT. We used the doping concentration that we know. So emitter is highly doped, base and collector are base is low doped and collector is moderately doped. So with this, we can determine VBI in each of these junctions. We did some questions on calculation of depletion bit and the reverse bias. So this is the formulation for that. It's very important. It again comes from the in between when we derive the Poisson's equation uh, to determine the electric field and potential. Some more questions on VBI and conductivity and resistivity. We discussed what is avalanche breakdown. So how and what is the temperature dependence of avalanche breakdown? It is as temperature increases, vibrations increase, and electron scattering increases, and electrons lose energy. So they have less energy to transfer to the lattice. So the avalanche effect reduces as the temperature increases, breakdown voltage increases. We saw what is the depletion layer. Again, some questions on the depletion with band diagrams. These are very important concepts. We also saw what is Zener uh, diode principle, that is due to this band-to-band tunneling for in very high input condition. How change in depletion will affect the capacitance in reverse bias. So all these questions are very, very important. Now coming to week 5 live session. In week 5, we saw the BJT's current voltage variation and mainly more about BJT, non-idealities, the small model, thermionic emission and current flow. So we did some simple calculations of the BJT using Abas-Mole's model, which is like a diode and dependent current source for both the junctions. So this is a very simple model with these few simple formulations, which is forward current and reverse current. So So just by solving these equations, we can determine any quantity. So there can be questions where you have to find this reverse current factor alpha uh, or the forward current factor alpha. We saw what is early voltage and how can we reduce early voltage. So early voltage is determined by from the output characteristic, and if we extend it where it intersects with the early or says in the voltage axis the early voltage, and how early voltage can be reduced. This is one of the most important concepts in minority carrier diffusion equation. It is very important to analyze the effect of recombination and generation and the different regimes of operation in the semiconductor in steady state or under different conditions. So this is very important derivation. We have some more questions on the uh, built-in potential between a metal semiconductor diode. These are simple formulations. We saw what is Schottky barrier, how it behaves with different work function, what is Fermi level pinning, what is how do we make ohmic contacts in practicality. That is when we dope it so the contact metal semiconductor contact so high that the barrier is so thin that the electrons can tunnel through it. This is the only contact. Some more questions on different relations on BJT. So these are some important parts, microscopic area diffusion equation, some relations on BJT for this week. So in the next week, in week 6, we had reached the starting of MOSFETs, which is an extremely important concept for modern semiconductors. We started with CMOS layout, how and or NOR operations are made in CMOS. This is very important. It's extremely simple but a very important concept. You can expect some questions from it in your exams. We studied the physics of MOSFET, what is the surface potential, what is the depletion rate, what are different regions of operations, what is inversion, accumulation. We studied all that. This is very, very important, extremely important concept. How bending happens, how bend y diagram changes, what is the y psi is equals to 2 phi f. All these concepts are very important. Some questions to determine Geox or Psys. So how KVL is applied in the MOSFET, the CV curve of MOS gap. It gives us a lot of information. So we determine CV, C of this, epsilon of by T of the accumulation, and T of can be determined through it. We studied what is the impact of charge carriers in the oxide, how they affect the threshold voltage, which is important. How the frequency dependent capacitance changes with the traps of the charge. Then simple the first order current calculations and saturation regime. Then again some CMOS questions to determine what is the function done by uh, this layout of transistors. Again questions on the maximum depletion rate of the MOSFET in MOSFET, consequences of changing oxide thickness, threshold voltage shift. So overall, in this week, the most important questions are MOSFET, electrostatics, and how what is surface potential, uh, what are different uh, potentials in the MOSFET, and how band bending occurs. All this is very very important. Now coming to week 7. In week 7, we discussed about the some classical transport theory, of distribution functions, Boltzmann transport equation, relaxation time, scattering, and mobility. We delve into the question straightforward, like uh, what is semi-classical transport? Electrons are considered as particles with effective mass, and effect of temperature and Fermi Dirac distribution, which is very basic. The concept of quasi-Fermi levels was also discussed, where Fermi levels defined in equilibrium and uh, quasi-Fermi levels defined in non-equilibrium. Then we saw impact of electric field on the distribution functions. With applied electric field, the distribution function are no longer equilibrium. Negative and positive side are not the same, and the distribution shift. We studied what Lowell theorem states. We saw the derivation of Matheson's rule and how different limiting mobilities affect the effective mobility of the electrons or holes. Some more questions on the ionization Fermi energy. Different, so this is very important for the dependence of temperature on scattering rate of different scattering mechanisms. Ionizability scattering decreases with increase in temperature. Optical phonon scattering increases. Acoustic phonon scattering increases. Piezoelectric phonon scattering decreases. So these are very important relations. Then we studied the Boltzmann transport equation. What is the Boltzmann transport equation? What are the different terms? It has diffusion term, dipole term, and collision. And the assumptions like it is semi-classical, it uses effective mass, the instantaneous collisions, there are no dependence of initial conditions, and no memory effect. We went back to the EK curve to see earlier we had seen what is the effective mass. It is dependent on curvature. Then we saw the slope of the EK curve gives us the velocity, group velocity of electron. Then we discussed some questions which has largest effective mass and which proportions. Lorentz force dependent on electric field as well as magnetic field, and the limitation of semi-classical theory. It misses out on some important quantum effects, that is the tunneling phenomenon and the quantum mechanical confinement effects. The dependence of mobility on the relaxation time. So this is all for uh, week 7. In week 8, we studied the diff diffusion model, perfect Riemann distribution, continuity equation, Taylor series expansion. So we saw the derivation of uh, diff diffusion model. What are the different density equations? This is the summary of the whole diff diffusion model. Some also recombination generation models. What are the different types of recombination generation models? What is radiative recombination, capacitive recombination? What are the assumptions in the diffusion model? It has assumes full ionization, non-degenerate nature, steady state, and isothermal constant temperature. Then we went to some numerical uh, methods, mesh sizes, uniform, non-uniform meshes, Debye length, relaxation time. What is the electric relaxation time? It's given by epsilon by sigma. N-type is preferred due to its higher uh, dielectric relaxation time. Then we saw continuity equation. Then the numerical methods are forward difference methods, central difference methods, backward difference method. We studied them in detail. What are the different methods? Why central difference is more accurate, but it has more complexities. Distillate boundary conditions, human boundary condition can create difference. Then the importance of non-uniform grids to capture the different behaviors in important regions, along with consideration of time, simulation time. There is a nice relation between the diffusion coefficient and mobility, DNF or known as native IP. Some questions over it. Again, some questions due to multivariate diffusion equation or continuity equation. So this was all about the diffusion model. In the week 9, we uh, talked about again some more part of diffusion model, special focus on the recombination generation model and some more uh, numerical methods. So this gives us a summary of the entire recombination generation model. Can be two particle interaction or three particle interaction. And based on the band gap, direct or indirect, we have different kind of generation recombination mechanisms. Either it is either it is radiative or non-radiative, that is thermal. Indirect is a two-step. It has uh, SRS, which is gap assisted or surface recombination. In three particle we have impact termination for the generation, and opposite of it auger is the recombination where three particles interact and transfer the energy. We saw what is band-to-band recombination. We what are excitons, that are electron and hole pairs bound together. Associated is SRS recombination. What are different mechanisms in SRS recombination is tap assisted electron capture, electron emission, electron hole capture and hole emission. SRS recombination rate calculations under low level and high level injection conditions. Very important. Again, more rate calculations. Some capture coefficient calculations, absorption coefficient, optical generation. Then what is auger recombination? It's dominant when there is high doping, as there are more number of carriers which interact and transfer energy to the third one to generate collision. Coefficients, units, it has very different units, centimeter to the power 6 per second, inverse of our recombination that is impact ionization. And this we had already discussed in previous assignments what is radiative and non-radiative recombination and what is their impact due to the band structure, direct and indirect band gap, conservation of momentum and conservation of energy. So that is all for this week. So the recombination rates and this chart as well as the doping dependence and uh, low level injection, high level injection dependence of rates is very important for this week. In the 10th week, we studied about hydrodynamic modeling and what is its importance. We first recalled the lift diffusion. With lift diffusion approach assumes thermal equilibrium, but there is no variation in temperature. Electron temperature, hole temperature is equal to lattice temperature. But we have to modify when there is temperature gradient. We can be delta T term. So what is saturation velocity, energy loss rate, momentum relaxation, the derived energy fluctuation time. So hydrodynamic model is basically considers two important concepts, velocity overshoot and carrier temperature dependence. We saw what is velocity overshoot, why it happens due to the what happens due to the uh, transient nature of electrons that nothing can change instantaneously. Limitation of hydrodynamic model being to solve uh, multiple partial differential equations at different intersection points of the grids. It's computationally expensive. Lithium diffuses that is ballistic transport where the length is so less that the wavelength is smaller than the mean free path. That means there will be no scattering within this LG band that is ballistic. It will shoot like a bullet. No collision or scattering. The relationship between different uh, coherence lengths, phase coherence length, elastic scattering length is driven by this length scales what determine diffusive transport or classical or quantum or ballistic transport. Balance equation, derivation, continuity equation, momentum balance equation, energy balance equation. So derivations are not important, just the results, as I keep saying again and again. The derivations in this course are not really important. This is an overview. So the conclusions and the results are extremely important. We should know where they come from. Just pay more importance on the theoretical parts. Again, discretization of hydrodynamic equation, different kinds of numerical methods where there are stability and the stability criterion for all those. Q4 triangle scheme, leapfrog scheme, which are explicitly stable or implicitly stable. Effective mobility, how it is derived from the linear current equation, field effective mobility. So, second last week, that is week 11. In week 11, we have discussed the quantum transport model, tunneling, Schrodinger equation, two particle potential step, potential barrier. So, this is very, very important lesson. That is, we started with the time the independent Schrodinger equation. What are the different terms? The kinetic energy term, potential energy term, total energy, sigma, size, the wave function. What are the different properties of wave function should be? The solution of Schrodinger equation is continuous, differentiable. Its derivative is also continuous and differentiable. Normalizable condition that gives us the psi gives us the probability density. We keep the derivation for particle in an infinite potential well. We determine what is this K. This is the formulation, then the solution of the particle in an infinite well, that is the wave function. Then we implied the normalization can be done to identify this A is root 2 by L. Then we found out what is the energy N square pi square is plus square by L square by 2n. It's very, very important. Solve some questions based on this. We studied what could be uh, tunneling probability is dependent on thickness of the barrier as well as the energy of the barrier. Again, more questions on normalization condition, transmission related questions, energy related questions, the discretization of energy, determining potential energy of magnetic energy for different conditions. So this is extremely important lesson. That is the foundation of semiconductors. And Schrodinger equation is a universal equation that has no derivation, but everything else is derived from Schrodinger equation. Is very, very important. And in the last week's lesson, we studied about commercial device simulation tools, models for disk diffusion, hydrodynamic simulation, recombination generation. So we started with an introduction to TCAD. So in the lecture video, Silvaco TCAD was discussed, and we discussed Synopsys TCAD in class. These are the two extremely important. Uh, these are the two extremely important question, simulators that are used commercially used by industry as well as academia. So TCAD is a setup of tools where we can do process simulation, device simulation, as well as circuit simulation, and the interconnection between these three. So what is TCAD? Computer technology, computer-aided design. It solves partial physics-based equations and partial differential equations to predict the device's electrical behavior. It is used for optimization of process for new technology. It cuts down on R&D cost and time and enables low-cost exploration and experimentation. We saw what are the different tools in the TCAD setup for some tools for structure generation, synthesis process explorer, structure editor, then for electrical measurements, figures device, and for visualization and synthesis as visual. The tool flow is we first make structure using process or a structure editor, then we do meshing. So the meshing is the grids where PDs can be solved, electrical characterization using as device, visualization using as visual. So the next process, it follows fabrication flow step by step. For instance, first device side will just make polygons to import polygons to make the final structure. The importance of meshing is number of nodes increases, simulation time increases. So we need to control meshing. We want our simulation to be accurate. That is a final mesh, but it should also take less time. So there is some trade-offs that we need to make. We import uh, fine mesh in important regions and coarse mesh in not very important regions to balance the accuracy and simulation time. We saw the S-device framework, what is the input and output, the commands, it has material properties and the biasing conditions, different physics models, and the structure. These are all the inputs and outputs is the uh, current voltage characteristics of different plot files and the distributions of different electrical parameters across the device structure in that plot files. And we saw a basic overview of the command file. We have different section, file section, electrode section, physics models, where different physics models are to be defined, and the important thing is the only relevant physics model should be defined, as different physics models can conflict with each other. Details of the terminal voltage uh, sweep are defined in the solve section. Different materials, how different materials can be imported in TCAD. We can define our own materials by defining um, their own parameter files. This is an example of parameter files containing different material properties, affinity, band gap, permittivity, and different physical model parameters, include parameters of mobility models, breakdown parameters, quantum confinement, etc., which are very important when calibrating models for accurate generations results between experimentation and simulation. This will be about mixed mode simulation where we define a netlist to connect different devices and simulate their circuit behavior. And we saw some basic questions on these. So this completes the course. We started with basics of semiconductors. We saw different devices first. Started with basic semiconductor theory, different lattices structures, density of states in semiconductors, and derivations for PN junction, BJT, and MOSFETs, which is very, very important. Then we went to different theories, semi-classical transport, diffusion, and quantum transport, hydrodynamic models, and then at last the simulations in TCAD. So we have discussed in every assignment, we have discussed only the most important parts, and it is very important that you see all the videos, solve all your assignments, and solve all the questions discussed in the live sessions by both the TAs. That will be very, very helpful for your exams. And the derivations for the last few weeks, like from week 7 to week 11, may seem very, very daunting as these are very difficult derivations. But as I said, these derivations are not important. Uh, uh, on their theoretical basis is important, their conclusions are important, their results are important. So keep them in mind. Whereas for MOSFETs, everything is very, very important. How everything comes, that is the physics of it. The derivations are important for MOSFETs, but for other theories, we can skip the derivations and take care of the results and the physics behind it. So with this, I conclude my presentation for the summary session. If you do have face any doubts, please feel free to contact me and email. You can email me always with any questions, even before and after your this course. And I wish you all the best for your exams. Thank you so much.